In today's walkthrough, we'll be going over question 1.3 on the week 4 worksheet. The problem states, in the following examples, Alice and Bob wish to send messages to each other, and Eve wishes to intercept that message. And RSA is either used incorrectly, meaning it yields an incorrect result, is used correctly but can be broken, or is both correct and cannot be broken. We're asked to select the option that best applies and explain. And we'll assume that P and Q are prime, and that Bob publishes the public key. Let's look at part A. Eve, Alice, and Bob share a menu. Bob asks Alice what dish she wants, and Alice responds with the name of the dish using standard RSA encryption. So the main thing to notice in this situation is that there's only finitely many menu items. So if Eve really wanted to, she could just encrypt every single menu item and see which one matches Alice's encrypted message. That match is exactly the menu item that Alice wants. So in this case, RSA is used correctly, but it can be broken. Let's look at part B. Eve is able to extort extra details from Alice and Bob. She also knows the values of P minus 1 times Q minus 1 times mod P. So if we think about the goal of the interceptor, or Eve, it's to find this value called D. And D is equivalent to E inverse mod P minus 1 times Q minus 1. So if Eve can find D, she can decrypt the encrypted message, basically. But is knowing P minus 1 times Q minus 1 mod P enough to do that? No, it's not, right? So RSA would be used, so RSA would be correct and can't be broken in this case. For part C, Bob selects E, where E is co-prime to N, but not co-prime to P minus 1 times Q minus 1. Okay. Once again, if we think about the goal of Eve, it's to find this value D, which is E inverse mod P minus 1 times Q minus 1. Right? And if E is not co-prime to P minus 1 times Q minus 1, then this inverse doesn't even exist. And so there is no D, there's no D. And that's not a valid, RSA. So RSA is used incorrectly here. Thanks for watching.